Right. Okay, so we'll have a quick review of nuclear physics. So we will be studying the properties of nucleus, basically. Entire chemistry deals with interactions of atomic electrons, whereas nuclear physics deals with properties of nucleus and constitution of nucleus. So nucleus is composed of protons and neutrons basically, and electron count is immaterial for this study actually. So we are starting with atomic number. What is that? Atomic number ante eno anukunnavandi? It is the number of protons in the nucleus. So atomic number or the nature of the atom is controlled by atomic number basically. Like the previous example, gold and mercury. So gold ante 79 atomic number, mercury 80. So if you remove one proton from the nucleus of mercury, you will get gold. So earlier the alchemists all tried to remove one electron from the, their utmost succeeded to remove an electron from the atom, but not from the nucleus. So if and only if you remove that proton from the nucleus, you will be able to change the nature of atom. So nature of atom is entirely controlled by number of protons. Okay. So even if the number of neutrons change, that doesn't matter, still the atom will be called with that particular name depending on the number of protons. So C612 is carbon 612, C613 neutron count periginappadiki still it is called as carbon. So neutron count doesn't matter, the nature of the atom is controlled by number of protons in the nucleus. Okay, so that's one thing. Next one is what? So nuclear constituents, number of protons, number of neutrons and total number of nucleons. That works. So total number of nucleons means total number of protons and neutron count. So we denote it by Z is the atomic number, A is the mass number, and difference of these two, A minus Z, is the number of neutrons. And X is the element. So based on this, the elements are classified into three categories. One is isotopes with equal number of atomic number. Atomic number same untadani isotopes annaru. Rendavadi isobars. So bar stands for mass somewhere, like barometer deals with the pressure exerted by air column on our head. So almost like mass of the air column. So isobars deals with same mass number. And third one is isotopes. Isotopes deal with same neutron number. And indulone special case isobars lo special case entante mirror nuclei. Mirror nuclei contains exchange number of otherwise number of A1 is equal to N2 and N1 is equal to A2. So the number of protons in the first atom will be equal to number of neutrons in the second atom. So proton and neutron count interchange. So example the example given was N713 C613. So here in nitrogen you have 7 protons and 6 neutrons, and carbon 6 protons and 7 neutrons. So exchangeable number of protons and neutrons count. The basic characteristics of mirror nuclei. Okay. So next property is the size of the nucleus. So this is the constituents of the nucleus. Size of the nucleus. So size deals with volume. So volume is proportional to atomic mass. Okay. So the volume of the nucleus is proportional to atomic mass. So in other words, the radius B is 4/3 pi r cube. So radius varies as 1/3 power of volume. That is why you can write R is equal to R naught A power 1/3. So you can write this. So how to understand this equation? Volume is proportional to atomic mass. So the volume of the nucleus increases in proportional to the number of nucleons. So when you keep on adding one by one nucleon, the volume increases proportionally. That means what? The separation between the nuclear particles is constant. So even if you add more and more number of nucleons, the separation should remain same. Separation between any two consecutive nucleons should remain same. Then only the volume increases proportionally with the number of nucleons. So but actually what happens? The missing point here is the number of interactions. Let's say you have 2 protons. How many number of interactions you have? You have 1 interaction. Now I am going to add one more. So I will be adding 2 more interactions. If I add one more proton, I will be adding 4 more interactions. 3 interactions. So the repulsive force count increases if I keep on adding more and more number of protons. So when the repulsion force increases, what happens? They start moving apart. But still, this condition is valid. So if we add one more proton to a particular nucleus, that means if you shift one atom next to level in the periodic table, what happens? The number of interactions increases enormously. Okay. So actual that exact number is what? N into n minus 1 by 2. So if my nucleon is the second one, how many interactions? 2 into 2 minus 1 by 2. How many interactions? One interaction. So if my particle is the third particle, 3 into 3 minus 1 by 2. I will have 3 interactions. If the incoming particle is fourth particle, how many interactions? 4 into 4 minus 1 by 2. 6 interactions will exist. So if I keep on adding an nth particle, I will be introducing n number of interactions more. What? Even more than that. So additional interactions count is what? So from second particle to third particle, 2 interactions additionally came into picture. From third to fourth, 3 interactions additionally came into picture. 3 minus 6. 3 additional interactions. Here, 2 additional interactions. So like that, if you keep on adding a particle, maybe n minus 1 number of additional interactions will come into picture. So what jaragali? The separation should increase enormously. And ఒక న్యూక్లియర్ వచ్చినప్పుడు ఒక ఇంటరాక్షన్ వస్తే ఓకే వ్యాలిడ్. But here n minus 1 number of interactions are additionally coming into the picture. So by now the separation should increase because there are more number of repulsive forces coming into the picture. Still, this condition is valid. So there is some additional mechanism that takes care of the volume of the nucleus, which keeps it proportional to the number of nucleons. So that additional mechanism on nuclear forces is a matter of discussion that we'll see in the next sessions. Okay. So for the time being, the most important factor is volume is proportional to atomic mass. In other words, radius is proportional to cube root of atomic mass. So still here the missing factor is how to deal with those number of interactions. Okay. So next property, mass of the nucleus and binding energy. So here comes the key factor, binding energy. So what is binding energy? And why do we need binding energy? Binding energy అంటే ఏంటండి? ఒక బాక్స్లో సమ్ ప్రోటాన్స్ ఏవో ఉన్నాయి, రిపల్సివ్ పార్టికల్స్ ఉన్నాయి, అండ్ యూ ఆర్ ట్రైంగ్ టు యాడ్ వన్ మోర్ పార్టికల్ టు దట్. ఏమవుతుంది? there will be more repulsive forces and the particle will be expelled out. అలా జరగకుండా ఉండాలి అంటే ఏం చేయాలి? when you have a group of repelling particles, to keep them together, what should we do? ఏం చేయాలండి? రిపల్సివ్ ఫోర్సెస్ ఉన్నాయి, కొట్టేసుకుంటున్నాయి, లేదు సెట్ ఆఫ్ మ్యాగ్నెట్స్ ఏవో ఉన్నాయి, రిపల్సివ్ మ్యాగ్నెట్స్, వాటిని ఒకచోట కూర్చోబెట్టాలి. ఏం చేయాలి? You need to push them together and sit together at some place. We need to apply additional force or consume additional energy to keep the particles, repelling particles, to sit together. అంతే కదా? సో ఇలాగే ప్రోటాన్స్ ఉన్నాయి, గ్రూప్ ఆఫ్ ప్రోటాన్స్. రిపెల్ అవుతూ ఉన్నాయి. ఏం చేయాలి? వాట్ ఈస్ ద పాసిబిలిటీ? You need to apply some binding force to keep them together. అంతే కదా, ఎక్స్టర్నల్గా ఒక ఫోర్స్ అప్లై చేసి వాటిని అక్కడ కూర్చోబెట్టాలి. ఎంతకాలం అప్లై చేయాలి? ఇలాగా ఫోర్స్ చేసి కూర్చోబెట్టారు. వన్స్ యూ రిమూవ్ దాట్, everything collapses. What is happening here? All atoms are stable, all molecules are stable. Who is that binding them? మరి ఎట్లా ఉంటాయండి అంత స్టేబుల్గా? ఎలక్ట్రాన్స్ ఇస్ నాట్ ఎ బిగ్ డీల్. ఎలక్ట్రాన్స్ ఆర్ మైన్యూట్ కన్స్టిట్యూయెంట్స్. అసలు దాని ఎఫెక్టే లేదు. ఐ మీన్ యూ కెన్ జస్ట్ రిమూవ్ దోస్ ఎలక్ట్రాన్స్, స్టిల్ న్యూక్లియస్ హ్యాస్ ఇట్స్ ఐడెంటిటీ. న్యూక్లియస్ అనేది బ్రేక్ చేయడం కష్టం. ఐ మీన్ దట్ ఈస్ వేర్ ఆల్ ద ఆల్కెమిస్ట్ ఫెయిల్. ఎలక్ట్రాన్ తీసేయడం చాలా ఈజీ, బట్ న్యూక్లియర్ని బ్రేక్ చేయడం చాలా కష్టమైన పని. దట్ స్ట్రాంగ్లీ బైండెడ్. వాట్ ఈస్ దట్ బైండింగ్ ఫోర్స్? సో ఇన్స్టెడ్ ఆఫ్ పుషింగ్ దెమ్ టుగెదర్ అండ్ మేక్ దెమ్ సిట్ టుగెదర్ by using additional external energy, option B is remove the energy. If you remove the energy from those particles, they don't find energy even to fight. అంతే కదా. Then they will sit together. Another option. అంటే మనకి ఇక్కడ జెమినీ సినిమా చూసారా? ఏంటంటే సినిమా స్టార్టింగ్లో కమిషనర్ ఊరికి రాగానే ఏం చేస్తారంటే, ఆ ఊళ్ళో ఉన్నటువంటి ఇద్దరు టాప్ మోస్ట్ ఛార్జ్ షీట్ ఉన్నటువంటి రౌడీస్ తీసుకొచ్చి అండర్ గ్రౌండ్లో వేసేస్తాడు. ఏంటి పరిస్థితి? వాళ్ళిద్దరు వాళ్ళు కొట్టుకొని చచ్చిపోవాలి, లేదా ఎవరో ఒకళ్ళు బయటికి రావాలి. సో ఈ కండిషన్లో దే చూస్ అన్ ఆప్షన్ సి. ఏం చూస్ చేసుకున్నారంటే, వాళ్ళిద్దరు కాంప్రమైజ్ అయిపోయి ఇద్దరు బయటకు వచ్చేస్తారు. సో దట్ థర్డ్ ఆప్షన్ వాట్ వీఆర్ ట్రైయింగ్ హియర్. ఇన్స్టెడ్ ఆఫ్ ఫోర్సింగ్ ద రిపెల్లింగ్ పార్టికల్స్ టు సిట్ టుగెదర్, we remove that energy. అంటే వాళ్ళకి ఒక 1 రోజులు తిండి పెట్టడం మానేస్తే ఏమైంది? కాంప్రమైజ్ అవుతారు. అప్పటి వరకు కొట్టుకొని తిట్టుకొని చచ్చిపోయి నువ్వా నేను ఎవరో ఒకళ్ళే బతకాలన్న కండిషన్ ఉన్నవాళ్ళు, when you stop feeding them, they got compromised. సో ఇక్కడ కూడా అదే, when you remove some energy from these repelling particles, they find no other alternative other than sitting together. That's not called as binding energy. The energy removed to keep a repelling particle together is the binding energy. So దానికోసం ఏం చేస్తారు? Will be removing energy from that. So it is the energy is what? Mass of protons plus mass of neutrons minus atomic mass. This is the binding energy. Total number of protons, total number of neutrons minus atomic number. ఇంకా స్పెసిఫిక్గా మాట్లాడాలంటే Z number of protons plus n number of neutrons mass minus mass of atom. difference of mass of all the protons and mass of all the neutrons minus the mass of the atom converted to energy is the binding energy. So here comes the specific property. Binding energy curve. So I take different set of elements from the periodic table. So as a function of atomic number. So atomic number changes, I'll get different elements in the periodic table. And I want to calculate the amount of binding energy required per nucleon. Okay. So this binding energy increases if I go on increasing the number of nucleons. So if for hydrogen binding energy is 0, I don't need any additional energy. And if I go to next level, helium I have 2 nucleons, 2 protons. So I require a certain amount of binding energy, and if I add one more nucleon, lithium, if I go to third element, I will be adding 3 new interactions. I mean n-1 number of interactions will be adding up continuously at every level. So the binding energy required also increases. And I need to balance 3 or n-1 number of interactions at every level. So binding energy per nucleon, if I add one by one particle, the binding energy also increases. Okay, after certain level, the number of neutrons count will increase. Maybe after 20. Periodic table, if you cross 20 elements, beyond that, number of neutron count increases. So they will balance some of the internal forces. And when you go to end of the periodic table, like 70, 80, 90, like uranium, all those higher order elements, neutron count is far more than the number of protons, almost double the number of protons. Take uranium. How many number of neutrons are there? 238 minus 92. Entende? Difference. 146 అంటే nearly 50. 56. So more than 50 number of neutrons are coming into the picture additionally. So they will balance some of the repulsive forces between nucleons, between the protons. So here we require less number of binding energy per nucleon because neutrons are balancing them. So I am dividing with A. So binding energy per nucleon reduces here when you go to uranium and all. Okay. So in between these two, where the atomic number is very low or atomic number is very high, excluding those two cases, for moderate number of atomic numbers, the binding energy is very high because they don't have less number of electrons and they don't have more number of neutrons. compared to these hydrogen and helium, they have more proton count, they have more repelling particles, and they have less number of neutrons. So proton count is high, repulsive forces are high, neutron count is low, the balancing force and the balancing mechanism is low. So they require higher binding energies per nucleon, whereas the rest of the elements require less binding energy because they have more neutron count. So when you break these atoms, like when you break uranium into two pieces, energy will be released. Why? You are developing a lightweight material, light atomic weight compared to uranium. But to realize that to keep those nucleons together, we require to remove more energy. You need to remove more energy. So you require more binding energy. So the difference of energy will be released as energy. So you require less energy to keep uranium atom together than iron or any other per nucleon. Similarly, if you travel from uranium towards barium and all, energy will be released. At the same time, if you travel from hydrogen, helium towards barium, even in that case also energy will be released. So one is fusion, another is fission. So in both the cases, energy will be released. So that additional energy is required to keep these moderately massive elements stable. Okay, so moderately massive elements in stable ga unchalante, you need to remove more and more amount of energy because they have more proton count and less neutron count. Okay, so that's about finding energy. Okay, Manna. Angular momentum parity. Okay, so these details we'll see in the next session. Other properties of the nucleus.